Hello, my name is Albert Wood. I work at the National Taiwan University and I study geometric analysis, in particular geometric flows, and in particular Lagrangian mean curvature flow. So today I'm going to be talking about singularities of mean curvature flow. In this first lecture I'll be introducing the subject of mean curvature flow and the study of singularities and giving an overview of the results in the field. And then for the next lecture I'm going to specialize to the case of Lagrangian mean curvature flow and demonstrate that the theory of singularities is quite different in that case to the generic case of mean curvature flow of Riemannian submanifolds. So to start off, I'm going to talk about what mean curvature flow actually is. So we're always working in submanifold geometry here. So we have an immersion from some abstract manifold n into some Riemannian manifold M with a metric G. An immersion just means that at every point of n, this map is an isomorphism on tangent spaces, but it's not necessarily an injective map, which would be an embedding. And because we are immersing this into a Riemannian manifold, we get an induced metric G. And then a very common thing to study is the variation for the volume functional. So the volume of the submanifold, as long as this is a compact submanifold, this volume is well defined, and we can look at the first variation, which gives us this formula here, where we pick some normal vector field to the submanifold inside M, and it turns out the first variation is given by the negative integral of this normal variation dotted with the mean curvature vector. And the mean curvature vector is the trace of this vector-valued second fundamental form, and the vector-valued second fundamental form is just the normal part of the ambient covariant derivative of the ambient manifold. Okay, so for example, a minimal surface is a submanifold, an immersion, a submanifold inside a Riemannian manifold such that the first variation gives you 0. So it's a critical point for the volume functional. And we can see just from this formula that that's equivalent to the mean curvature being 0. On the other hand, we can also consider the gradient descent. So if we pick our normal variation here to be the mean curvature vector itself, then this will be the most efficient decrease in volume among normal vector fields of the same L2 norm. So this inspires the definition of mean curvature flow, which is where we consider now a family of immersions that move by the mean curvature vector. So at every time the derivative of this family of immersions in the time direction, in other words, the variation in time, is given by the mean curvature vector. And so this is the most efficient decrease in volume, or the gradient descent of the volume functional. So the first question is, what actually happens under this flow? And I think it's best illustrated with a sequence of examples. So the most basic example we can give is the most symmetric example we can give, which is the shrinking sphere in Rn+1. So here we work with an ambient Euclidean space, and we choose our submanifold to be dimension 1 less. And the reason this is convenient is that then the mean curvature flow equation becomes a scalar equation in the radius, because since the mean curvature vector is always normal to the submanifold, we can dot the mean curvature flow equation with a choice of normal vector to get a scalar equation. In this case, the symmetry of the situation also means that the equation reduces to just an equation in the radius, which if you calculate the mean curvature turns out to be dr by dt equals minus n over r. And then this is solved quite easily as r equals root of minus 2nt, picking the initial condition of the radius is 0 at time 0. Okay, note this is a self-similarly shrinking solution to mean curvature flow. In other words, it moves by homothety or scaling. There are more self-similarly shrinking solutions to mean curvature flow, and if you have one, then it satisfies this equation here. The flow at time t is equal to some scale factor of the flow at a specific time, say time -1, and you can create an equation for this factor and find out it has to be root of negative t. And then you can also prove that it must satisfy this equation here. Mean curvature vector must always be equal to the normal component of the position vector divided by 2t. So more generally, the situation of convex hypersurfaces, so a hypersurface is one dimension lower than the ambient space, so this sphere is a hypersurface in Rn plus 1. And more generally, if you have a convex hypersurface, then we have very similar behavior. Gerhard-Huisken proved that a convex closed embedded hypersurface in Rn shrinks to a point in finite time. I'll explain what is meant by a round point in later in the talk. So the second most simple case after just a sphere is if we pick the dimension of our submanifold to be 1. So we are dealing with an immersed circle. And in this case, the situation is almost completely solved. We have that this theorem of Grayson that says that if we have a mean curvature flow of a one-dimensional submanifold in a two-dimensional Riemannian manifold, also known as a curve shortening flow, then the two behaviors are either the flow exists for all time and converges to a geodesic, or it collapses to a round point in finite time, exactly like the sphere does. So this first case is what we would like to see from mean curvature flow. The mean curvature flow is the gradient descent for the volume functional, so we might hope that the mean curvature flow is a way that we might find minimal submanifolds. But as we've seen with the sphere example, that isn't always the case. If your homology class is trivial, then it's just as possible that your flow dies off in finite time, forms a finite time singularity. Note this theorem is about embedded curve shortening flows. If you have an immersed curve, like this figure 8 here, then this does not collapse to a round point in finite time. Instead, it forms a different kind of singularity, which we'll expand on more later. So another very nice case to consider, and one that I've been studying quite a lot, is the case of equivariant mean curvature flows in Cn, by which I mean flows with an ON symmetry. Explicitly, we consider an embedding L of S alpha equal to A of S alpha, B of S alpha, where we have identified Cn with Rn times Rn, where this alpha is a parameter in the sphere in Rn, Sn minus 1. So this can be thought of as a curve in C, the As plus IBS, and then you take this and you rotate it with an SON action in Cn. If we consider this C to be the C times 0 to the n minus 1, the first C factor in Cn, then we can recover this entire manifold up here by rotating this thing around C using the action of SON on Rn times Rn, where it acts individually on each of the factors. So the reason that studying motion of submanifolds of this kind is nice, just as in the sphere case, is that the symmetry is preserved under the flow. So the study of the motion of these types of submanifolds, equivariant submanifolds in Cn under mean curvature flow, can be reduced to the study of an equation, a flow of the profile curve, gamma equals A plus IB. Here is an example. So here is an initial condition on the left. Due to the fact that this alpha can be, if alpha is in Sn minus 1, then minus alpha is also in Sn minus 1, so there always turns out to be a Z2 symmetry across the origin on the profile curve. So this is an example of a profile curve, and under mean curvature flow of the corresponding equivariant submanifold, the behavior is as it looks like on the right here. So the black is the initial condition, and this thing descends to the origin and actually forms a finite time singularity. This might look a bit strange because mean curvature flow moves in the direction of the curvature, and you might think that the curvature direction is moving outwards like this because it's convex, this curve. But of course, there are lots of curvature directions that we're not seeing that result from the equivariant directions. So you should think about there being a sort of circle joining these two curves like this. And this curvature is actually stronger than the curvature of the profile curve itself, which is why we're getting this collapse to the origin. So this is another example of a finite time singularity of mean curvature flow. There are a few specific nice examples of equivariant mean curvature flow. So here is a self-expanding solution to mean curvature flow. So this is the profile curve on the right here. The initial condition is in red, and this thing actually moves away from the origin by self-similar expansion in the same way that the sphere moves by self-similar shrinking. Here is a self-similarly shrinking solution to equivariant Lagrangian equivariant mean curvature flow. If we start with a circle, then of course that symmetry is preserved under the flow, and so this thing shrinks down to the origin. Okay, so we've had lots of examples. So as I mentioned before, we might hope that it exists for all time and converges to a minimal submanifold, since it's the gradient descent for the volume functional. But what actually happens is that often we get singularities occurring. So studying these singularities is very important, and a natural question might be, how many different kinds of singularities can we get, and what do they look like? Can we classify them? And can we tell when one will happen and when we'll get long-time existence? So a natural way to study singularities is to perform a blow-up procedure, so we can examine the infinitesimal behavior of the singularity. So restrict for convenience to the case where the ambient manifold is R to the n, and let's say a singularity happens at some space-time point x0 capital T. Then what we can do is consider the parabolic rescalings, where we translate our flow to be centered on the space-time point x0t, and then we scale by lambda in the space direction and lambda squared in the time direction. And the reason we do it like this is so that the resulting flow is still a mean curvature flow. Now, we've essentially zoomed in on the singularity a little bit, the singularity x0t, by kind of pulling in the canvas. So if we do a sequence of such rescalings, we hope to capture the infinitesimal behavior of the singularity. But of course there might be a problem there, because there's no guarantee that this sequence of rescaled flows will actually converge to anything. We might get curvature blow up, for example, in which case we wouldn't have a C2 convergence to any limit. But if we assume this type 1 curvature bound, where the modulus of the second fundamental form is bounded by some constant over the root of t minus t, capital T minus t, then this condition is preserved under parabolic rescalings, and so we get a uniform curvature bound on compact subsets of spacetime. And then by an Artzela-Ascoli argument, we may extract a subsequence of this rescaling sequence, which converges smoothly. So taking a subsequential limit gives us some model of the singularity, which we call the type 1 blowup. And if we have this curvature bound, we say the singularity is a type 1 singularity. In the case where we don't have this curvature bound, then we won't, if we perform this rescaling sequence, then we will in fact get curvature blowup at times before the singularity as the sequence progresses. So we won't get smooth convergence to a flow, and we say in that case that it's a type 2 singularity. So let me give an example. So here is a picture of the space-time track of a mean curvature flow. So this four-leaf clover is the initial condition, and we can see that very quickly it regularizes itself and becomes circular and then shrinks to a point in finite time. And on the right is the type 1 blowup. So what we do is we focus in on this, we focus in on this point at the end here, the space-time singularity, and we perform the parabolic rescaling, and we essentially end up seeing the infinitesimal behavior of the flow at this point, and we see that it looks very, very, very similar to a shrinking circle, the closer and closer you look. So, in the case of a type 2 singularity, which do happen, I'll give an example in a second, then the type 1 blow-up procedure may still be performed, but we don't get a convergence to a smooth mean curvature flow anymore, but instead we get convergence to a weak or brachy flow. There is still a way that we can recover information about the nature of the singularity, though. What we do is, instead of focusing in on the space-time singular point and performing our parabolic rescalings focused there, we track the point of highest curvature on a sequence of times leading up to the final time. And we perform our rescaling around the point of highest curvature at those times and scale by a factor such that the maximum of the second fundamental form at that time is equal to 1 over the manifold. So explicitly, we take a sequence of times tk tending to our singular time, capital T, and we define ak to be the maximum of the second fundamental form over the manifold at this time, and then we perform a rescaling around the point xk, which we choose so that the second fundamental form is maximized at that point, and we perform the rescaling with factor ak, so that the maximum of the second fundamental form at that time is now 1. There's a few details I'm missing out here, but that's approximately the idea, and what we end up with then is an eternal solution to mean curvature flow, the type 2 blow-up, which has a maximum of the second fundamental form equal to 1 at all times. So you always get a smooth blow-up by construction. But we're no longer centered on the space-time singularity. So we're no longer looking at the infinitesimal behavior at the singularity. Here's a good example. So the figure 8 that I mentioned earlier, I mentioned that it doesn't form a round point. Instead, it forms a different kind of singularity, where the whole figure 8 actually collapses together to a point. It actually becomes more and more narrow as it is approaching that singularity. So if we focus on the singular space-time point, which is the origin here, and perform our type 1 blow-up, we don't get a smooth flow, because in fact this is not a type 1 singularity. What we end up with is this double density plane. So we end up with just a straight horizontal line with density 2, where the convergence is in the sense of varifolds. Instead, if we pick a sequence of points and times so that the second fundamental form is maximized at that space-time point, and perform our sequence of rescalings around those points, then instead we get this solution, which is a translating solution to mean curvature flow known as the Grim Reaper. So in other words, at the point of highest curvature, as the singularity forms, our flow is looking more and more similar to this Grim Reaper solution to mean curvature flow. For more information about the Grim Reaper and translating solutions, you should check out Weibo's talk, which is also about mean curvature flow and singularities. Another example, so in this equivariant situation that I described earlier, we have a type 2 singularity. If we perform a type 1 blow-up at the origin, we get a pair of lines through the origin. From the perspective of the profile curve, you can see this is actually a sequence of type 1 rescalings, and you can see that it's approaching more and more closely just a pair of lines. If we view the actual submanifold, this is a pair of n-dimensional planes in Cn. And if we perform the type 2 rescaling, focusing in on a point of highest curvature, which will be right on the tip here, then instead we end up getting this minimal equivariant submanifold known as the Lawler neck. You can again see it approaching more and more closely a hyperbola. The profile curve turns out to be a hyperbola, and this is a projection of the actual two-dimensional submanifold. In the case of a two-dimensional manifold inside C2, this is a projection of the Lawler neck, the limiting type 2 blow-up, down into R3. So this is an example of a type 2 blow-up where we end up with a static eternal solution to mean curvature flow as the type 2 blow-up. So bizarrely, the singularity is more and more closely modeled on a minimal submanifold as the singularity forms. So the second fundamental form is blowing up, but it's actually not obvious that the mean curvature is blowing up, given that the model is has mean curvature 0. So one important thing to mention about the parabolic rescalings is that they leave self-shrinkers constant. They preserve self-shrinkers. So this is easily seen by the equation for a self-shrinker. Ft equals root of minus t f minus 1. So if we rescale now around the singularity, which is at space-time point origin 0, the equation is f lambda at time s is equal to lambda times f at time minus lambda to the minus 2s. This is the original flow, this is the rescale flow. This is just how they're related. But then we can use the fact that the original flow was a self-similar shrinker to write it as root of minus lambda to the minus 2s times f at time minus 1. And then these lambdas here cancel out, and we just get root minus s times f at time minus 1. So we see that this is a self-similar shrinker with exactly the same immersion at time minus 1. So it is exactly the same flow. Another way of thinking about this is to say that self-similar shrinkers are their own type 1 blowups. So they are their own singularity models. And in fact, much more is true. It's actually true that all type 1 blowups of type 1 singularities give you self-similar shrinkers. And this can be seen using the rather amazing Huysken monotonicity formula, which I'll now talk about. So to state it, we need to consider the following weighted backwards heat kernel on R to the m, the ambient space. So it's just the same as the standard backwards heat kernel, except that it's weighted with this minus n over 2. There would usually be an m over 2 here. And the reason that this is a sensible quantity to consider is that it has this parabolic rescaling symmetry. So here's the theorem. So if we have a flow ft and a rescaled flow f lambda s, where it's rescaled around some point x0, t0, sorry, there's a typo here, this should be a t0, with the new time related to the old time by lambda squared. Then we have this relation between the integral of the this weighted backwards heat kernel over nt and the integral of the backwards heat kernel over the rescaled manifold. And we can also throw in any function on the abstract manifold here if we like. So just as an example of an application of this, if we have some self-similar shrinker, so the rescaled flow is just the same as the original flow, and we choose our point that we're focusing on to be the singular space-time point, origin 0, then this integral of this kernel is equal to the integral over the rescaled flow by this theorem. But then also the rescaled flow is just the same as the original flow, but at a slightly different time. So you can therefore see that this quantity, the integral of this kernel over our manifold at time t, actually is independent of the time t. So this function is constant in time. Moreover, this quantity in general is monotonic. So this is the Huysken monotonicity formula. So generally speaking, the derivative of the integral of this kernel is equal to some negative quantity. And the integral here, you can see, is precisely 0 for a self-shrinker centered at the point x0, t0. If x0 and t0 were both 0 here, we have the equation for a self-shrinker that I showed you earlier. There's also a version of the Huysken monotonicity formula where we plug in a function here, and we just get the heat equation on the function on the right-hand side as well. So we still will get a monotonicity as long as we have here a subsolution to the heat equation as our phi, and that will come in useful later as well. So this theorem is used to prove the fact that I just mentioned, which is that a type 1 blow-up of a mean curvature flow at a type 1 singularity is a self-shrinking solution to mean curvature flow. I'll quickly demonstrate why that's true. So the idea is that the Huysken monotonicity formula tells us that the derivative of the integral of this heat kernel, which I will just write as a capital phi, is equal to minus this quantity here, and I'll assume that everything is centered at the space-time point 0, 0 for convenience. So if I sketch first, just as an intuition, the graph of this quantity here, I'll call this theta, then theta kind of goes down. It doesn't need to be convex. It just goes down like this until the singularity at time 0. So now if we perform a parabolic rescaling, we know that parabolic rescalings keep this thing constant. I mean preserve the value of this thing. So if we do a parabolic rescaling, I'll just depict it, then what happens is the point 1 gets pulled back to the point lambda. So if this is the graph for our original flow, and this is the graph for our rescaled flow, And because the values of this quantity theta correspond, the graph will look like this. It'll look much shallower in the rescale flow. So what that means is that if we continue doing this rescaling over and over and over again, then in the limit, if there is a limit, the type 1 blow-up, we will get just a flat line here, assuming some minor regularity on this function theta. And if it's a flat line, then what that means is that the derivative of this quantity is equal to 0. And if this is indeed equal to 0, then that tells us that h is equal to x perp over 2t, which is the same thing as ft being a self-similar shrinker. More explicitly, if we define this capital theta to have a couple of parameters, to be the integral over the rescaled flow at time minus r squared of this kernel, then that means that we have the theorem, the symmetry of this quantity over, under parabolic rescaling tells us that theta of lambda r is equal to theta of 1r. So if we have a 1 here, that's just the integral over the original flow. So that means that, in particular, theta of 1 lambda inverse of r minus theta of 1, 0, this is equal to theta of lambda r minus theta of lambda 0, which is equal, by Houston's monotonicity formula, if we integrate this formula, this is equal to the integral from 0 up to, it's equal to the integral from minus r squared up to 0 of the integral over the rescaled flow of this h plus x perp over 2s. Yeah, these should be squared. DHN. But now, as long as this theta is continuous, then as lambda tends to infinity, this tends to 0, and so therefore this quantity tends to 0 as lambda tends to infinity, and this implies that as long as we have a smooth convergence, so all of these quantities are converging nicely, we must have that the mean curvature plus x perp over 2s is equal to 0 for the limiting type 1 blow-up n infinity s. Okay, so this tells us that actually there aren't very many singularity models. There are just as many singularity models as there are type 1 blow-up, as there are self-similar shrinkers, sorry. So here are some more results. Huysken conjectured actually that generically we only get spheres and cylinders as type 1 blow-ups of singularities. So I didn't mention any other examples of self-similar shrinkers, but there are in fact many more. For example, there is a torus in R3, a two-dimensional torus that is a self-similar shrinker under mean curvature flow, known as the Angenate torus for the person who discovered it. And Huysken conjectured that these examples are pathologies, that we can perturb away from these examples linearly and just get spheres and cylinders. And Colding and Minikotzi proved a theorem to this effect, which is that in the hypersurface case, all other singularity models can be linearly perturbed away. I should say this is for embedded hypersurfaces in Euclidean space. So Colding and Minikotzi showed that the only linearly stable singularities are the spheres and cylinders. A more difficult question is to ask whether generic mean curvature flows only encounter spheres and cylinders, which is different to linearly perturbing the singularity itself. And progress towards this has been made by Chodos, Choi, Mantelidis, and Schulze recently, where they show that if we assume a couple of popular conjectures on the nature of singularities, then we do only get spheres and cylinders for generic mean curvature flow. Type 2 blowups are much more difficult to study, and it's not actually known what form type 2 singularities take in general. We saw earlier that there was an example of a type 2 singularity model on a translating solution known as the Grim Reaper. And it's generally thought that type 2 singularities should be translators or static solutions or more generally solitons. But there has not been a result of this effect even in the hypersurface case yet. And finally, why do we want to study singularities? Why do we want to study singularities at all? One reason is that we might hope to use the mean curvature flow to prove Poincare conjecture style results, like topological results for submanifolds. And one example of a result in this direction is of Huisken and Sinistrari, who used a knowledge of the finite time singularities of two convex mean curvature flow, which is a strong condition, to show that you can perform a surgery at every singular time and continue the flow with a knowledge of how you've changed the topology of the object. And in particular, they show that any smooth, closed, n-dimensional, two-convex immersed surface where n is greater than or equal to 3, must be diffeomorphic either to Sn or some finite connected sum of s to the n minus 1 times S1. And if it's embedded and simply connected, it actually must be a sphere. Okay, so that's the end of the first lecture. In the second lecture, I'm going to change tack and talk about Lagrangian submanifolds. Lagrangian submanifolds, it turns out, are actually preserved by mean curvature flow. Which means that mean curvature flow is a viable tool for use in studying Lagrangians and special Lagrangians. And the singularities in that case are also very interesting because very much unlike in the generic mean curvature flow case where we only get spheres and cylinders, we'll see that the singularities of Lagrangian mean curvature flow generically are completely different. So I look forward to seeing you there.